MapReduce. Think of MapReduce as a simplified way to solve big problems using a divide-and-conquer approach. You break down a problem into smaller chunks, map, process them independently, and then combine the results, reduce. This is akin to using a high-level language like Python or Java, where you focus on the logic rather than the hardware details. From an analogy perspective, MapReduce can be likened to a system that creates its own character set, using key-value pairs, akin to how key encryption involves transforming data into a secure format. MapReduce can be seen as a software framework or a programming model that facilitates the process of distributed computing for large-scale data processing tasks. Analogy: imagine a large workshop where many workers collaborate to assemble complex products. Each worker, machine, specializes in a specific task, and they communicate through a structured process overseen by a coordinator, MapReduce framework. Workers, machines represent individual machines in a cluster. Tasks, map, and reduce functions correspond to specific jobs each worker performs. Coordinator, MapReduce framework oversees the entire operation, distributing tasks, managing communication, and aggregating results. Purpose: like workers in a workshop, each machine in a MapReduce cluster handles a part of the dataset, product, processes it according to defined tasks, assembly instructions, and collaborates to produce the final result, finished product. Even though sophisticated statistics and machine learning are enhancing the possibilities for knowledge extraction from data, many if not most data analyses for decision support rely on descriptive statistics using SQL for grouped aggregation. SQL is also used in the field of big data with MapReduce technology. In this sense, although SQL database technology is quite mature, it is more relevant today than ever. Descriptive statistics in SQL refer to techniques and queries used to summarize and analyze data to understand its main characteristics. While SQL, structured query language, itself is primarily used for querying and manipulating data within relational databases, it can be leveraged to compute basic descriptive statistics such as counts, sums, averages, minimum and maximum values, and more. Descriptive statistics in SQL are commonly used in various applications such as business intelligence, data analysis, and reporting. They provide quick insights into datasets without requiring extensive data extraction to external tools for analysis. SQL's ability to handle large datasets efficiently makes it suitable for computing these statistics directly within database systems. When you perform a search in software that interacts with a database, such as a search engine, e-commerce platform, or any application querying a database, it often utilizes descriptive statistics techniques in the background to retrieve and present results efficiently. Descriptive statistics like sums, averages, counts, and aggregations help in sorting and ranking search results. Search engines often rank results based on relevancy metrics calculated from these statistics. For instance, showing products with higher average ratings or more sales first. Efficiently retrieving search results requires optimizing SQL queries using aggregate functions like sum, count, avg, etc., and indexes. This optimization ensures that the software retrieves and processes data quickly, even when dealing with large datasets. Some software applications may perform deeper statistical analyses to provide insights into search trends, user behavior, and performance metrics. These analyses help in improving search algorithms and user experience over time. Non-relational database technologies, which find more and more fields of application under the generic term NoSQL, differ not only superficially from the classical relational databases but also in the underlying principles. Relational databases were developed in the 20th century with the purpose of tightly organized, operational forms of data management, which provided stability but limited flexibility. In contrast, the NoSQL database movement emerged in the beginning of the new century, focusing on horizontal partitioning, schema flexibility, and index-free neighborhood with the goal of solving the big data problems of volume, variety, and velocity, especially in web-scale data systems. Horizontal partitioning, also known as sharding, involves splitting a large dataset into smaller, more manageable parts called partitions or shards. Each shard is stored on a separate server or node within a distributed database system. This approach allows NoSQL databases to scale horizontally. By distributing data across multiple servers, NoSQL databases can handle large volumes of data and high read/write throughput. Improved performance. Queries can be executed in parallel across shards, enhancing overall database performance. Enhance fault tolerance. If one server fails, data remains accessible from other shards, ensuring high availability. Schema flexibility in NoSQL databases refers to the ability to store and manage data without a predefined schema. Unlike relational databases, which enforce a strict schema, table structure with fixed columns and data types, NoSQL databases offer dynamic schemas. Each record, document, column family, etc., can have its own structure, and fields can be added or removed without affecting other records. Support for diverse data types. NoSQL databases can handle structured, semi-structured, and unstructured data efficiently. Adaptability. Schemas can evolve as application requirements change, facilitating agile development and accommodating diverse data formats. Index-free querying, or sometimes called index-free adjacency, is a characteristic of certain NoSQL database models, such as document stores and some graph databases. It refers to the ability to retrieve data directly through traversal or direct access without relying on traditional secondary indexes. Direct access. NoSQL databases store related data together, making it possible to retrieve related data efficiently without the need for complex indexing structures. Traversal. In graph databases, relationships between entities, nodes and edges, are stored explicitly, allowing for efficient navigation and traversal of the graph structure. Performance benefits. Index-free querying can lead to faster read operations compared to traditional relational databases, especially in scenarios involving complex relationships and hierarchical data. NoSQL database movement emerged with the goal of solving the big data problems of volume, variety, and velocity, especially in web-scale data systems. Big data refers to datasets that are too large and complex to be processed using traditional data processing applications. The three V's, volume, variety, and velocity, are key characteristics that define the challenges and opportunities associated with big data, especially in web-scale data systems. Massive data generation. With the proliferation of connected devices, sensors, social media interactions, and digital transactions, data volumes are growing exponentially. Storage requirements. Storing and managing terabytes, petabytes, or even exabytes of data becomes a significant challenge. Scalability. Systems must scale horizontally to handle increasing volumes of data efficiently, often requiring distributed storage and processing solutions. Structured and unstructured data. Besides traditional structured data, like database tables, big data systems deal with unstructured data, e.g., text, images, videos, and semi-structured data, e.g., JSON, XML. Data from multiple sources. Integrating data from diverse sources such as social media feeds, log files, IoT devices, and user-generated content presents challenges in data integration and interoperability. Data formats. Managing different data formats and schemas requires flexible data models and processing frameworks. Velocity refers to the speed at which data is generated, processed, and analyzed in real time. This includes streaming data, continuous streams of data from sources like IT devices, financial transactions, and social media updates. Real-time processing, requirements for real-time or near real-time analysis and response to incoming data. Low latency, systems must handle data with minimal delay, making high-speed data ingestion and processing critical. While big data poses significant challenges, it also presents opportunities. Improved insights. Analyzing large, diverse datasets can uncover valuable insights and patterns that were previously hidden. Innovation. Big data fuels innovation in areas like machine learning, AI, predictive analytics, and personalized user experiences. Enhanced decision-making. Real-time analytics enable organizations to make data-driven decisions faster and more accurately. The following characteristics distinguish information from material goods. Representation. Information is specified by data, signs, signals, messages, or language elements. Processing. Information can be transmitted, stored, categorized, found, or converted into other representation formats using algorithms and data structures. Calculation rules. Combination. Information can be freely combined. The origin of individual parts cannot be traced. Manipulation is possible at any point. Age. Information is not subject to physical aging processes. Original. Information can be copied without limit and does not distinguish between original and copy. Vagueness. Information can be imprecise and of differing validity, quality. Medium. Information does not require a fixed medium and is therefore independent of location. These properties clearly show that digital goods, information, software, multimedia, etc., i.e., data, are vastly different from material goods in both handling and economic or legal evaluation.